Okay. So, so how do I press this to move on? Oh, this one. This one.
This one.
Yeah. Okay.
This one. Yes.
Yeah. Okay. Well, thank you very much. Oops. Okay. Yeah. Yuri's first visit to DTU, Technical University of Denmark, was in March 1993, and his last visit in November 2017. So this was almost 25 years. And during these 25 years, we managed to publish 85 joint publications and 3 unpublished. This was all on mathematical physics, nonlinearity, solitons, and chaos theory with applications to superconductions, optics, and optical communication, and molecular dynamics and biomolecular dynamics, and in the very last years also traffic dynamics. But I'll take the starting point in the tunnel effect from quantum mechanics. So here you have the Schrodinger, the time-independent Schrodinger equation with the propagation constant k and potential u. If you take the delta function, delta potential, then it's well known that the solution should be continuous and have a discontinuity of the derivative. So then the solution for the incoming and reflecting and transmitted wave is well known. This is a textbook example, and this forms the continuous spectrum. And then we have the discrete spectrum. There's a pole at k equal to minus I rho 2 divided by 2. And the constant here can be determined by normalization. And the application of this solution in soliton theory is a well-known nonlinear mapping by inverse scattering transform, by which the continuous spectrum becomes radiation and the discrete spectrum becomes soliton, or if there are several poles, then several solitons. So we posed the question, what happens to the scattering problem if you choose delta prime instead of delta, the derivative of the delta function? And this, we worked on that together with Sasha also and Ermakov, and it resulted in this paper here, where we found out that when we replace delta by delta prime, you cannot integrate any longer, so you have to regularize, replace the delta function by such a distribution like this one here, and the delta prime function has to be replaced by this one or this one here, where there are two parameters, epsilon and L, both tending towards 0 in the limit of the delta prime function, the area being kept equal to 0. And here we found, we believe it's a new result, that there was a complete reflection for most values of the amplitude.
Hello.
No transmission. And then there were a set of an infinite set.
Hello.
Yes, can you hear me? Ah, okay. An infinite set of values of the sigma parameter in front of the delta function, for which there was resonant tunneling, resulting in a reflection coefficient given by this formula and the transmission coefficient by this formula here. And then these values of sigma is determined by the intersection between the tan H function and the tan function, which you can get already from Google. So this was a very lengthy calculation in the paper, but a very elegant perturbation technique was suggested to us by Oliver Penrose, who is an older brother of the Nobel Prize winner. And so we leave an exercise for the listener. What happens to the nonlinear soliton mapping if you apply this to the delta prime problem? Well, we moved on and looked at delta potentials in the Dirac equations, set of two first order differential equations. And here we published this paper with Yuri. And presently, we are actually investigating the phenomenon of Klein tunneling with other Dirac equations, with delta potentials, and also coupled Schrodinger equations with delta prime potentials. The method of Penrose was also applied to this problem here with the beam equation, force order Euler equation, Euler-Bernoulli equation, where we considered potentials delta, delta prime, and delta double prime, and delta triple prime. And delta triple prime is interesting because when there is this, when the derivative of the delta function is one order lower than the order of the differential equation, then you have resonant tunneling. Also in this case here, it becomes very complicated, but you can find the solutions to a complex equation where you have the resonant tunneling, and the solution are given by, maybe you can see this here, intersection between the zero curves for the real part of the sigma and the imaginary part of it. And this actually made the front page of that journal, that year, Journal of Physics A, where we published this. So during his last visit, Yuri, instead of considering a single wave number incident on the Schrodinger equation, he was looking at a wave package instead in the time-dependent Schrodinger equation with this initial condition here. And then he used the Laplace transform with respect to time, and Fourier transform with respect to space. And you all know how skilled a mathematician Yuri was. So he obtained the solution for an arbitrary initial condition corresponding to the incident wave package. And this was in terms of a convolution integral of the wave package and the complementary error function. So we're trying now to solve this problem also with delta prime instead of delta, but have not been successful so far. Now I'll move on to another of the many papers we wrote together. This was on discrete one-dimensional nonlinear Schrodinger equation with long-range interactions, and we used that as a model for energy and charge transport and storage in biomolecules. This was work in collaboration with Mengelejew and Johansson and Kim Rasmussen. And oops, sorry, now I have to go back again. So we use this Lagrangian where U, and this is the kinetic energy, M is the mass of the base pair in the DNA chain, and UN is the complex amplitude of the inside. And then the intra-base pair interaction is given by this expression here, but I'll give this potential in a moment. And the inter-base pair interaction is given by this expression here. And for the interaction, we would typically use a potential function here. Then you can choose the parameter, the power S here. If S is infinite, it corresponds to nearest neighbor approximation. But if S is 5, it's a quadrupole interaction, and S equal to 3 is a dipole interaction. And then we were introducing the rotating wave approximation, and then the system reduces to this set of equation here, where the Lagrangian is given by this term and the Hamiltonian by this these two terms here, and the effective dispersive energy is this term, and then the intra-base potential could either be a Morse potential or a Leonard-Jones potential, but we, for just to get an insight, used a simpler nonlinear potential, namely this one here. And so you obtain from the Hamiltonian the dynamic equation in the usual manner. And here are the equations. So this Hamiltonian is a conserved quantity, and n is also the number operator, and the number of excitation is also conserved. And then we look at the stationary solution where psi n depends exponentially on time, and we have this frequency lambda, and in this case we get this set of equation here, and here we observe a bistability of the stationary states, and this shows up in the following way. If you map the number as function of this frequency, then if we have nearest neighbor coupling, that's a full curve, so that's a monotonic function. But if you choose S, the parameter S equal to 3, for example, this is the dipole-dipole interaction, then you'll see that you develop a curve which is not monotonic, but you have actually, it goes up here and comes down, and different values of S is plotted here. And so for a single value of n, there will be 3 intersection points. So you have the possibility of bistability with the solution which correspond to this value and to this intersection point, but the intermediate intersection point is not relevant because that's unstable due to and Spacek, maybe all other authors also. And here you see the resulting dynamics. There's a switching from the continuum-like state. You see here, that's the continuum-like state. It's broadened out. This is the along the chain here, and this is the time. And you see, as time progresses, the continuous state localizes into a localized state. And this happens when you give it a small perturbation. But you can also choose another perturbation for the same parameter values, and then the localized excitation will develop into a continuum excitation. And the continuum excitation is movable, while the localized solution is the fixed solution that doesn't move. So we actually consider this phenomenon as the possibility, this stability phenomenon makes it possible to model energy storage and transport on the DNA molecule. The phenomenon is due to the competition between the nonlinear dispersion expressed in terms of the ratio n/j and the radius of the long-range interactions. Yes, but then we were not satisfied with that. We went on to make long-range interaction with curvature, and this was another paper with Sergei Mendeleev. And here we used this Hamiltonian, but now the sites are placed in a plane with position vectors Rn. So the z coordinate is equal to 0, and you vary x and n. And here are the resulting equations, with this Catch-Baker dependence on the long distance term, and n is also a conserved quantity. So here you see a picture of our curved model of the DNA. The distance between the two pairs, the two base pairs, between the set of base pairs doesn't vary, but there's an interaction between long-range interaction between the sites. This is a continuum version of the dispersion function and a continuum version of the mass function of the base pairs. And you see there's a double hump solution here. So as a result, you again find a dependence of the number operator on the frequency, which is monotone in the case where there's no curvature, kappa equal to 0. This is the dot dashed line. But then if you introduce curvature, then you can see that you have the case again with possibility of bistability, and there are two solutions, a solution and an asymmetric solution. And what's interesting is also that the Hamiltonian, the total energy of the system, decreases as you increase the curvature, both for the asymmetric solution and for the symmetric solution. So that means that the energy of the excitation of the DNA molecule would tend to localize at points where there is curvature, and then when it localizes, it enhances the possibility of breaking the bond between the two bases in the base pair. So we also studied how an incident wave package hits the maximum point of curvature here, and this is the time development for a low value of the curvature. Actually, I think it's well, it's not 0, but it's a small value. And then when you increase the curvature, you see that the incident wave package stops at the place where the maximum of the curvature occurs, and then you further increase, it starts to be reflected, the incident ray, and then for a high value, d equal to 3.0, which is a little bit more than you would have in the dipole-dipole interaction, then sorry, this is nonsense what I'm saying. This is nothing. It's a curvature which is about 3, then you will have a full reflection of the incident wave package. And here is the velocity of the wave package plotted as function of the curvature. So if you have a small value of the curvature, then you will see that you have a positive value of the wave. So it's still progressing. And then for increasing curvature, it will stand still at the maximum value of curvature. And then for even higher values of the curvature, the wave package will be reflected and have a negative velocity. So we also did work on two-dimensional nonlinear Schrodinger equations, but Jens-Juul Rasmussen, my colleague who's sitting next to me here, will deal with this work together with Yuri, and Mads Peter Sørensen, who will speak, maybe he is the first speaker after me, but he will deal with the work we did on the curved sine-Gordon equation for the Josephson diode, and also for nonlinear oscillating shock waves. But in the very recent years, as I mentioned in the beginning, we started to work on traffic problems, dynamics of vehicles with sensors, and pedestrian dynamics. And we managed to finish 5 papers there, and a 6th paper was unfinished. I think I still have time to say a few words about, it can only be a few words about the last paper here, which was published, Pattern Formation in Flows of Asymmetrically Interaction Particles, Peristaltic, we call it peristaltic pedestrian dynamics as a case study. And here's the paper. You see that there were many authors, the collaboration was extending all the time. Yuri worked together with Mads Peter and Jens-Juul, and this professor we had Jens Starke and his student Christian Marsler. Yes, and the dynamics of the pedestrians was modeled as n particles with position vectors Rn in a plane xn, yn, and as function of time, and the motion was then governed by this first order equation here, where the v function is the intentional velocity of the pedestrian along the x-axis, and then there's a force with which the nth pedestrian is repelled from the other pedestrians. I shall define that force in a moment. And then there's another force, which is, so to speak, the walls of the channel in which the pedestrians are moving. So that kind of limits the motion of the pedestrians in the y direction. So the force is given by a regular symmetric term where we have, which is the derivative of a repulsion potential, but there's also an asymmetric term in the force term, which is given by this little complex expression. But I'll just mention the reason why we have this. You know, it's not the same thing for two pedestrians. If you hit a pedestrian on his front, it's different if you hit him from the backside. So this makes a very interesting problem, because then when you have this asymmetric law, then Newton's third law, action equal to reaction, is not valid any longer, and you get some very, very interesting problems. And this, we were just at the beginning of going into studies of that kind of problems when Yuri passed away. Here is the potential in the y direction. So you see that it will make the particles, the pedestrians, would preferably be along the x-axis where y is equal to 0. But there is a possibility to move away from the x-axis also. And here we look at the solutions to the equations then, and we call it free flow solutions when the particles have the same constant velocity and there's equal spacing between them. And in this case, we find two types of free flow solutions: one-lane solutions and two-lane solutions. In this picture here, we have replaced the number of particles by color. So here we are in running from minus capital N half to plus capital half approximately. And that replaced that, illustrating that by colors. And in this simulation here, they form a nice one lane on the x-axis where y is equal to 0. But then if you change the parameters a bit, then they form, then the pedestrians would like to move on two lanes. And maybe you have observed that also when you're moving in a sidewalk in the busy streets of Kiev. I don't know, but if you move on with the parameters, strengthen the interaction between the pedestrians, then there will be a zigzag configuration here between two subsequent pedestrians, and so it looks like that. And this was what, and this moves ahead, and so that was what we named peristaltic motion. And then you can strengthen the interaction further, and then there's not any system in the ordering anymore. So here, as I said, the color indicates the pedestrian number. So this was a short reminiscence of the many, many papers we did together. These 25 years with Yuri were unforgettable for all of us. Thank you very much, Larissa and the whole committee, for inviting me to this conference honoring the memory of Yuri Gaididei. It was a fantastic privilege to work with Yuri. Thank you.
Thank you very much, Peter, for warm talk about Yuri, for your thanks also. And it was an honor for us that you accepted our invitation and joined this meeting. As I told, 25 years of collaboration with Yuri and 33 years of knowing you. It's a great privilege to all of us. And the last part of your talk was really interesting because I remember once Yuri came from Denmark, and during the coffee break, he told about a new field of interest, this study of traffic and pedestrian movement. But we never, unfortunately, at least I myself, never had listened his talk in details. And I know that there is another scientist from Yuri's circle, also a collaborator of Vadim Loktev, Yuri Pestriakov, who worked in this area. For Ukraine, this subject is really very interesting, and that's not my opinion, but also my opinion. But that was a phone call from Vadim Loktev, who said, well, for Ukraine, that is so important.
Yes.
And I hope that the next time you will tell us in more details. Sorry that I have taken time, but I had to announce in the beginning, we do not intend to have the formal meeting with strict schedule. You have to stop, you have no time for questions. So please, feel free. And now the session is open for questions and then for comments, please.
May I ask a question?
Yes, yes, of course, and Marigorich.
My question relates to the DNA. You used very interesting the nonlinear system for description of soliton dynamic in this DNA structure.
Yes.
But my question is concerned the parameters which you used to estimate the effect. Where you choose the parameters?
Yeah, this is a little bit complicated to, so may I suggest that I simply send you the paper we wrote on it, so you can see it there. I think it will take a long time to go through all that, for there were many assumptions. Essentially, we followed the Perard-Bishop scheme and then added these various effects. But I think we have in the material, in the book, abstract book, we have your email address, and I will be happy to forward this paper to you if that's okay.
Good.
So, sorry, two questions, if it's possible.
Sure.
Can we see slide 47 or 49, please?
Oh, yes, we'll try to 40.
Oh, yeah. For 49, for example.
49. Okay.
This one.
Here value n, large n, exists maximum for this value or no?
Sorry.
Maximum for n, large n.
Yeah.
The maximum.
I think it's
Capital N. Exists maximum for this value?
maximum. Yeah, well,
There's no maximum for capital.
there's actually no maximum in a sense. I have forgotten what number we used in the simulations. Was it about 100 or something like that?
Yeah, at least.
At least, yeah. Jens, who is a co-author on this, also thinks that it was about 100 we used in the numerical simulation. But this is okay. But we don't have we didn't work out a continuum model. No, we didn't do that. So there can be a lot of work done in this area, in particular when you don't have Newton's third law. That opens up a whole new area of research, which is this can be a model of many other physical fields than just traffic dynamics.
Thanks. And the second question, is it problem, maybe a slightly naive question, but is it problem that here you have a basic nonlinear Dirac or Schrodinger equation, which is not inverted in time? As a result, maybe, for example, you don't know exactly when vibrations or kinks appear or disappear regardless of the boundary condition resonator?
Yeah.
Is it a problem or no? Absence of inverting in time of nonlinear Dirac or Schrodinger equation.
Yes, this is a very, I think it is a Hamiltonian system, so it should be possible. Can go back here,
Ja, dus nej, ja, den. Nu er det.
No.
Så går du tilbage.
Oh, sorry, it's the wrong way. For example, this one here.
Yeah.
I think it's time reversible. That would be my immediate answer, because we have an I in front of the dt.
Mm-hmm.
Thank
you.
Do you agree, Larissa?
Thank you very much. Very interesting
Okay.
report.
Well, for time-dependent Schrodinger equation, because we have psi and psi star complex conjugated, then the time symmetry is preserved.
Okay. Yes.
For Dirac equation, I think also, because of the complex conjugation of the wave function.
Yes, right.
Thank you very much.
Yeah. But this is a very important point, in fact. Played a lot of roles for the conservation of energy in the system.
Yes. Well, of course, we don't take into account the in some problems, this is the dissipation effects.
Yeah. Okay, but there are numerous studies on Davidoff solitons with dissipation and a long struggle on stability towards temperature of the Davidoff solitons. And I don't know if you're aware that Nitan Kenkra has just published a big monograph with his scientific work through the times. I think it's about 600 pages or something like that. And there's a whole chapter devoted to the discussion about the temperature stability of Davidoff solitons. I'm not sure it has appeared yet, but I know that he has sent it to the printer because he asked me to read through it. And this was a big task. He gave me, I think, half a week to do it. And so try to read 700 pages in 3 days, which is impossible, of course. But it'll be a great thing when this soon appears, that book.
You know, I didn't know about this book. Thank you very much for mentioning. I will try to track it. Other questions, please.
You are quoted a lot there, Larissa, your works.
Thank you. Other questions, please.
A question about traffic problem. Also, we did not work with Yuri in this direction. However, he told us many times about this. And one thing which he was really excited was creation of solitons in traffic of cars.
Yes.
And the amazing thing is that the soliton can move in direction opposite to the motion of cars. Yes. So now question about these pedestrians which repulse each other. So there is a force, repulsing force.
Yes.
Is it possible to get some solitons in this system as well?
Yeah, already in the, I don't remember whether it was this one or this one here. This was a car problem where we had sensors, you know, adjusting the distance between the cars. And then some Japanese had performed a big experiment. They had a big circles where they had cars driving around in that circle. And then it turned out when they had the these cars driving around in this big circle, a big field with this experimental work. Then it turned out that they formed, they didn't keep the distance in the free flow distance, but they formed solitons. So the free field movement there is unstable. So Yuri developed a theory for the lack of stability. So this you can find in the early, I'm not sure, either this paper or maybe this paper, these multi-jam solution. The jam in this theory, in this field here, the jam is a soliton.
Yeah. So this is a kind of self-focusing of traffic.
Yes. It's a well-known phenomenon, and we actually had a contract with was it Toshiba? It was one of the Japanese car producers, because they wanted to develop sensors for cars so they could, keep the distance and so forth. And but it turned out to be a very intricate, complicated problem.
Yes.
Very interesting. So yes.
It's not a free flow. There are traffic lights. There are different psychological aspects of drivers and so on.
Yes, and we were also considering to do, multi-lane problems with traffic light and everything. But there's, even though Yuri worked day and night when he was visiting, he worked all the time, and I think one thing he enjoyed in Denmark when he was visiting in Denmark was that there was no administrative work. We did all the administration, for him. So he had plenty of time, and so the only break he would take was around noon. He would take a walk around in the campus here, and maybe all the way down to our seawater down to Öresund, and have a swim there, even though it was in the fall or something like that. So he was a great visitor. It was a pleasure.
Yes.
All the time.
Indeed, he was also so sportive person. He played tennis. He liked running,
Yes.
swimming.
Yes.
Yeah. Thank you very much, Peter. Any other question? No. Sorry.
I have a very short question.
Yes, please.
This theory and simulations for the DNA molecules, how is the relation to real biological systems where you are dividing the DNA chain for making protein molecules? Are there any relation there, or is that documented?
I haven't, I must confess, I have not followed that literature in the recent years. So I hope there is, there is in principle this thing that you require a certain energy to break the bonds between the two chains. But I can't answer your question whether the parameters we find, and starting with the parameters we put into the various terms in the equation, how well they relate with the actual physical measurements.
Okay.
But I know that Perrin and Bishop, they for a long time, tried to make bridges to the experimental community in biology, but how successful they ended up, I don't know.
Okay,
well,
thank
that
you.
is a very complex subject.
Yeah.
Okay, so let us thank Peter for very interesting talk again.
Thank you.